This is EGR 101, third in our series of Revolutionary Engineering and Engineers, Professor Henry T.Y. Yang, and bringing finite element simulation to engineering. Good morning and welcome back to EGR 101. We're going to talk about the third in our series here of Revolutionary Engineering and the engineers that brought us these revolutionary updates. This is Professor Henry T.Y. Yang, and this concerns bringing finite element simulation to engineering. So let me just show you what we're talking about here. This is a representative beam, similar, in fact, identical to the one that we analyzed a few weeks ago when we looked at how Stephen Timoshenko brought calculus to engineering. Now, in this case, it's a different method for analyzing this beam. So Timoshenko used a small piece of material cut out from the beam. He analyzed it based on calculus and came up with an equation for the maximum stress. Another approach, which uses the computer and something called linear algebra, allows us to analyze the same beam in more than one axis. In this case, the x, z, and even the y if we so desire. This finite element solution is similar to the calculus in that it's looking at a small piece of material. The difference is because it's using linear algebra and the computer, it can solve thousands and thousands of simultaneous equations all at one time to give us an answer. What that results in is a much more detailed picture of the stresses in the beam. So you can see the color coding here shows the stresses in the beam. If I compare that to Timoshenko with calculus, he could only work in the one axis here. And so his formulas were limited. They're still very powerful and very useful, but they were very limited. Now, the reason I bring this up is that every aspect of engineering uses finite element in some way. It dominates current engineering simulation and analysis, whether it's mechanical, electrical, mining, materials, civil, you name it. I think I'm forgetting a few people in there. But even chemical, this dominates the engineering that they're doing, and it's why I wanted to bring it to you. One of the leaders of this was this gentleman here. His name is Henry T.Y. Yang. He was one of the very first doctoral students to actually get a degree in finite element analysis. He was influenced by Timoshenko. Timoshenko was his hero. When he graduated, he came to Purdue University, started it as a very young professor, and he began work to advance finite element analysis. Part of his work involved the nuclear, the analysis of reactor pressure vessels, and also containment systems. He did work that could not have been done any other way. The other big thing that he did is he published multiple papers, and he taught on this subject in very simple, easy to understand terms that brought it to engineering students and practicing engineers. One of the engineering students that he endured was me, and I peppered this poor man with many, many questions over the time I took 4 courses from him. My big issue was the following. He would do a finite element solution, then compare his work to what Timoshenko had come up with using calculus. If they were very much in agreement, he would conclude that he had been successful. I kept making the point that his simulation here using three axes of motion was actually more representative of reality than the calculus solution, and that we really should be comparing his work to experiment. He gave me that smile like you see right here, and told me, very interesting, that would be a good bit of research. So he went on to publish multiple papers and bring this work to engineers such as myself. He later became the Dean of Engineering at Purdue, and now is currently the Chancellor of the University of California at Santa Barbara. So when you think of finite element analysis, think of this man. And that's all on this topic. Stay tuned for several other videos which teach this week's lesson. Thank you, and we'll see you in a few minutes.